Okay, good afternoon. Hope the lunch was good. Not good? It was good? So how many are sleepy? Otherwise everyone will sleep. Most of the lectures are conducive for sleeping, no? Right? It's a hard time to teach. I mean, hard time for anything immediately after the lunch. So I should have asked them to prepare a not so good lunch then to keep you. Curd is missing? How come curd gets missed, yeah? It's missing really? Yesterday and today? Huh? Curd will make you sleepy. Yeah. Curd makes you more sleepy. Curd rice. Though it was not intentional, but it seems like it's helping. Right? Okay, so let's come back to fundamentals of process-based hydrological modeling. Now, from last 1.5 days, we have been talking about hydrological cycle, eco-hydrology, how ecosystem and water cycle interacts, and we say that it's important for us to understand, for us to plan, right? Well, all good. Conceptually everything is fine. How do you tell your computer to do that? How do you tell your computer that your hydrological cycle is this and this is what I want? Providing the thresholds, proper data sets. Okay. What else? Correct. We build a mathematical equation for the natural system, right? At the end, your computer does not understand whether it is a watershed, whether it is a hydrology, whether it is ecosystem, environmental system, or biosphere. It understands only zeros and ones. Any computer or any model, it understands only zeros and ones, and you need to communicate in that way. So your SWAT model is a combination of mathematical equations. So you see in the hydrological process, runoff, SCS curve number method, it basically transforms the rainfall to runoff through a set of mathematical equations. Penman-Montier method, it represents the evaporation process mathematically, that given these inputs, you will have this much of an output. Now we have seen them individually. Many of these processes are seen more of in an individual way. How do we combine them to develop a watershed model? Is something that is where the link comes, right? So there are many number of models. Okay, so probably more than 1,000. I think minimum 200 watershed models are there. Watershed based model, minimum 200 watershed based models are there. Each have their own assumptions, their own mathematical way of representing the natural processes. They have certain way of representing or some assumptions, or take only certain processes which are important, right? Now, one of the things that we should be careful is what model should I choose. It continues from our morning discussion, right? You cannot just choose a model just because it's available to you. You know it, your research group knows it, or your supervisor knows it. You need to see what model is suitable for your application and why is it. Only then you have to go and choose a model, right? So for example, SWAT, most of the studies, SWAT is used only for the stream flow estimation or stream flow prediction. To be very frank, why to use such a comprehensive model just for stream flow? You can do a much better job by using a machine learning algorithm to predict the stream flow, or a simple, more simplified model, HMS, will still get the stream flow predictions, right? Okay. So let's see that. Let's see some, give you a brief overview, right? And hope you don't sleep in this process. The key message that we want to have at the end of this lecture is you should be able to classify the hydrological models based on the process description, have some understanding on the development of hydrological models where we interlink different hydrological processes, okay, and also you develop a understanding on model calibration, validation, and sensitivity analysis, okay. So various processes in developing and setting up the models, right. So coming to the first question, what is a model? Some of you would have seen this parts of the slides, but yeah, let's see. Anyone, what is a model? Mm-hmm. Yeah. Okay. Anyone else? What is a model? Mm-hmm. Okay. Yes. Any model, whether it is physical or mathematical, is basically a replica of a system. Okay. So a model is a product, physical or digital. You have hydraulic models. How many of you have seen the flumes? Hydraulic models. Yes. I think most of you would have seen in your fluid mechanics laboratory. They are physical models, or a digital model, which is basically a mathematical or computer based simulation models that represents a system of interest, okay. So a model is similar but a simpler version of that system, okay. So much of your natural system, for example the watershed system as it is quite difficult and complex to represent it exactly, right. In the morning session, Professor Chaube was mentioning that 1 gram of soil will have billions of microbes. Now it is very complex and difficult to represent that 1 billion microbes in 1 gram of soil in a mathematical sense. Well, we can do that, but the complexity keeps increasing, right. And moreover, the spatial variation, what is the soil and soil components that you have here, how does it vary, it just becomes too complex, right. So we generally have a simpler system. That is something that we need to understand, especially the modelers. Most of us, we do modeling by assuming that whatever the model output we get is the true value. It is the absolute truth. Let me tell you, most of the times models does not give you the absolute truth. Rather, they are very abstract. So you have to have an understanding that it is a very simplified system of a real world system, right. So a good model is a judicious trade-off between realism and simplicity, right. So there are different models, as I said, and one of the reasons different models have been developed in the hydrological or watershed models is because there are n number of assumptions. For some people a certain assumption may be valid, for others assumption may not be valid, right. So in that sense, the numerous models are developed, and depending upon your application, you need to have a trade-off between how realistic you want to be and how simplified you want to be, right. And we will come to that. We will come to that some of this realistic and simplified ways when we talk a little bit more about SWAT, when we are trying to set up for an Indian condition. How many of you have seen the agricultural fields in India? Oh, good. At least all of you have seen. At least 90% have you seen. What is the size, usual size of one plot? plot size, usual plot size. You will have the bund constructed, right? Depends on the farmer, how much area he has, but on an average. Less than 1 acre. Yeah. Even if you have 1 acre means you are a big farmer, right? Almost you had a good land. Okay. Can someone convert 1 acre to square meters? 4,000? 1 acre, how many square meters? Google it. We do 4047 square meters, right? Now 4047 square meters, right? So on an average we can say 20 by 20, 20 meters by 20 meters plot. Now what is the land use map that you have? What is the resolution of that? ESRI 10 meters is more recent one, right? But before that, 30 meters. If you take NRSC, it's 56 meters, right? Which is at a much higher resolution. And before NRSC, we used to go up to 500 meters by 500 meters. The global land use, I am sure many of you would be using the global land use, which is 500 meter by 500 meter. Now, how much of the realistic land use gets represented in that 500 meter by 500 meter or even 56 meter by 56 meter? Probably nothing, right? Okay. Now, in that model, if you come and tell me that I am getting a 95% accuracy, so is it right or is it wrong? What is wrong in that? 95% accuracy is good. Original parameters are one way, yeah, we'll come to that. 95% accuracy is good, right? No? Why is it wrong then? Scale, okay. Right. So physically you know that whatever we are representing or giving input to the model is not a same as what is there in the field. Now how does the model come up with a 95% accuracy? Yes. 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 So that is where I come back to this part, whether the result is good or bad. If you are interested in stream flow, in accurate prediction of stream flow, 95% accuracy is good. I am not worried about whether my evapotranspiration is getting simulated properly, whether my groundwater recharge is getting simulated properly, or soil moisture gets simulated properly, right? And that is where I say you don't need SWAT for that, right? You don't need a model that comprehensive. But 95% accuracy in stream flow prediction is not good if you are interested in the intermediate part. How well am I representing my crop growth? How well am I representing the nutrient transport? Or how well I am representing the sediment transport in the model, right? So depending upon the application, your model, so that is where the realism and simplicity. If you want to develop some solutions and want the system to be realistic, then you have to go more to realism as compared to simplicity, right? This is just one of the examples, okay? Now modeling, well, it's a process of developing a model, and simulation is basically a process of using the model to study the behavior and performance of an actual or theoretical system, right? So we simulate SWAT model, right? We simulate the SWAT model. to study the behavior or performance of a real world watershed, to understand how the processes are occurring or what are the changes. Okay. So, most hydrological models represent this hydrological cycle. This is a figure I keep using in many of my lectures, whether it is applied hydrology or whatever course I am teaching. So, this system gets represented in either a physical system. How many of you have seen a hydrologic bench? Anyone? Rainfall simulator. Rainfall simulator is usually in the actual field, but this is a hydrologic bench. Basically, it will have a rainfall simulator, it will have a complete watershed, it will have measurements, you can change the soil, you can change this thing, right, and you can measure everything. So, some of the simplified representation, but it cannot match the scale, it cannot match the scale. And in hydrology nowadays, it is very seldom used unless for some, to show it to the students that these are all the processes that are happening, it is seldom used. So, we develop a mathematical expression, we develop a mathematical expression for this entire process as a y as a function of x1, x2, x3, x4. Now, this y can be anything, it can be stream flow, it can be evapotranspiration, it can be soil moisture, or it can be the groundwater recharge or groundwater flow, waste flow, lateral flow, any flow that is occurring, you can develop a mathematical relationship, right. So, most of the models in hydrology focus on developing this particular cycle in form of this. And we have seen some of the models. SCS curve number method is a model. Penman-Montieth method is a model where you relate your inputs, precipitation and temperature to evaporation. In SCS curve number method, we relate precipitation to runoff by considering land use, soil and slope as other factors. Okay. So, need for hydrological model, I do not want to go into that, most of you know this, right. We apply for various purposes, flood forecasting, management, drought management, reservoir operation, inflows to the reservoir, watershed management, rainwater harvesting, or improving water quality, sustainable development, design and operation of hydraulic structures, design and management of water supply, irrigation management and control, right. So, coming to the hydrological model, we are trying to develop this particular expression where y is a function of x1, x2, x3. So, it is basically most of the models will give stream flow as a function of precipitation, infiltration, evapotranspiration, soil moisture and groundwater flow in general, right. Most of your models output, though you get other outputs, most of your watershed based hydrological models have stream flow as a function of precipitation, infiltration, evapotranspiration, soil moisture and groundwater. Now, some models consider all the variables of your hydrological cycle, some models consider only few of the variables, right. It is not necessary that all the factors get considered, right. For example, some of the conceptual models GR4J, HBV, they consider only precipitation and potential evapotranspiration, and they represent the process completely differently as compared to what SWAT does or what VIC does, right. There is some similarity between VIC and GR4J, but in general there is a difference in the way it gets represented or how HHMS represents these particular model simulations. So, coming to the classification of hydrological models, we can broadly describe them into process description based on process description, spatial representation and then randomness, right. Now, all these methods that we are talking about when we want to quantify the hydrological process, they have to be applied at certain scale. Now, at a watershed scale, how do we apply? Curve number, what do we do? SCS curve number method. If you have a different land use, different soil classes, we take a weighted average curve number. Yes. So, what are we doing by weighted average curve number? So, we are defining a one curve number for the entire area. So, essentially we are kind of lumping the system, we are representing the entire system as a single unit, right. So, how do we represent these processes is what we cover in spatial representation. Do we discretize the basin and represent it differently, each component, or we merge everything and represent it as a single unit. Second one is process description. Are we using some laws of physics? Most of your water resources, hydrology or fluid mechanics runs on the laws of physics, right, or can be described using laws of physics. You have conservation of mass, conservation of momentum, and conservation of energy. Based on these three, you can describe any of the processes. So, are you using some of the physical laws to describe the processes? That is what we call as physics-based hydrological models. Then conceptual models are which have been based on our conceptual understanding. We have some understanding of the process, and based on that, we have developed a mathematical expression, right? SCS curve number method is partly conceptual. I won't say it's fully conceptual, it's partly. Based on our some understanding, they have developed a particular process, right? And the third one is empirical. Empirical is, what is empirical models? Using the experimental data. That is the characteristics of empirical equation, right? But what is the empirical model? Yes. So, essentially in empirical model, you have data of independent variable and the dependent variable, and you develop a mathematical relationship between them. Most of your machine learning models are empirical. They develop a nonlinear regression, right? Any regression is what is your AIML, right? Simplified regression, right? If you just simplify them, it is regression. Only thing is, it does regression at a different scale, right? It considers far more interactions between the parameters. Now, coming to the spatial representation, you have lump, where you consider the entire unit as one, semi-distributed, where you still break down, but the individual units you still consider as to be single unit, and then you have distributed models which you can describe for the entire catchment, right? You have different parts, and based on the randomness, it's deterministic model and the stochastic model. Okay, let's see each one of them before we go further. So, as I said, physics-based models are the models which use the laws of physics to describe the hydrological processes, right? So, it uses the differential equations describing the physical laws of mass, energy, and momentum conservations to solve. There are models, hydrological models, which solve the hydrological processes by solving the differential equations, right? And differential equation solving usually takes time. It's an iterative procedure. For many of these equations, there is no exact solution, right? It's always an approximate solution, and it takes time. Now, it represents the process more accurately, but it also takes lot of time for computation, right? So, now we have a mobile phone with what, 16 GB RAM? Yes. Okay. So, when these models were getting developed, I would say 512 MB RAM, a very floppy disk, right? And we had a very limited computational power. So, this particular physical-based models, they started developing using water balance equations, basically using the conservation of mass. Change in storage is equal to input minus output, a more of a systems-based approach, right? And that is where SWAT, HMS, and Mike Shee, they are all there. So, SWAT, you can say it to be a physics-based model, but it also uses a lot of empirical equations. We call it physics-based because it works on water balance equation. It works on the equation that change in storage is equal to input minus output, where input is your precipitation, output is your runoff, evapotranspiration, groundwater flow, and groundwater recharge. Okay. Conceptual models are also known as gray box models, right? And they have a descriptive representation of hydraulic system. This is a representation of GR4J, right? This is GR4J, yeah. So, you have a modulus understanding, right? We have been talking about different systems. Each one of us, if I ask you to represent a process in your own way, there may be some variation. There may be some commonality, but also there may be some variation. So, based on our understanding, based on how different people perceive, your models have been developed, right? So, they are developed based on observed or assumed empirical relationships, among different hydrological variables, right. So, GR4J, HBV are some of the models which are called as conceptual models. Empirical black box, which develop a relationship between input and output. A neural network is a good example of an empirical model, right. So, yesterday we saw different models, right. Horton's model, what is it? Is it a physics based model, is it a conceptual, or is it a empirical? Conceptual? Sure. Empirical? Conceptual? Answer is varying depending upon how sleepy you are. Right? Horton's model. Yes, correct. True. So, he derived the wave based on the experiments, but he observed that it follows a decay function, and based on that he has come up. Although initially it was developed as an empirical curve, but over a period of time, more experiments, it became more of a conceptual model. Empirical are basically applied location specific, and that's the K parameter. K parameter is soil specific, but then if you see in general it follows the conceptual framework, right. What about Penman-Montieth? Is it empirical, conceptual, physics based? Yes. How many of you say Penman-Montieth is physics based? Remaining are not sure. It's physics based. It is derived using conservation of momentum and conservation of mass and conservation of energy equation. Your Penman-Montieth can be derived by applying Reynolds transport theorem. Okay. What about rational method, rational formula? Rational formula is empirical? Yes? Yes? I would say it is derived. It's a simple model, but it's derived, right? It equates input to output. At the time of concentration, your input to your watershed is rainfall intensity. What is this rainfall that is coming, right? Some millimeters per second or centimeters per second or centimeters per hour. That multiplied by the watershed area gives you the volume flow rate that is coming in. And we have our understanding that some part of that goes to runoff. Yes. So, a fraction of that, what we call as runoff coefficient. Now, how is it empirical? Yes. Q is equal to CIA. Since it is CIA, units are not matching, it is empirical. Huh? Units will not match, units will match. There is a factor that needs to be changed, right? Okay. So, depending upon the process, that's good that we have done this exercise to classify them into different models. Okay. Now, coming to the spatial representation, you have these models. Now, at what scale do you want to apply? Can anyone tell what is the maximum scale your SCS curve number method can be applied, or a rational formula can be applied? Do we know that there is a maximum limit for area that it can? For which one? Rational formula is how much area? 5,000? 5,000 is too much. It is either 50 to 80, between 50 to 80. Huh? hectares, huh? I'm pretty much sure it's not going to be square kilometers. 5,000 square kilometers is a huge area, right? What about SCS curve number method? It's also more or less similar, right? Now, when we are have to simulate a large catchment, probably in some places thousands of square kilometers, some places it is lakhs of square kilometers. How do we represent them, right? So there are three different ways of representing. One is your lumped model. One is your lumped model, where we consider the entire catchment to be a single unit, a single computational unit, right? That is, the entire catchment behaves in one particular way, right? So given a rainfall at this particular point and given a rainfall at this particular point, it is going to behave exactly same, and that is what is lumped. Lumped models treat the complete basin as a single homogeneous element and develop a single outflow hydrograph. Now a little bit more detailed version is your semi-distributed model. Semi-distributed model is you derive your catchment, distribute it in the way you want to. There are different ways of doing it, and those distributed units you consider them to be single. For example, this catchment is now divided into 3 subbasins, 1, 2 and 3. Now I can show the variation, or I can put the variation among these 3, but within this subbasin it is still a single unit, right. I am not showing the variation within this within a particular subbasin, but in the entire watershed I am showing it into 3 different ways. The last one is fully distributed. Fully distributed is also, again, you see entire variation, probably a grid based model, right. Now the question comes, which model should I consider? Which is the best one? It depends on the purpose of the model. Okay. Data availability, right. Okay. Anyone else? Yes. This is only one computation per day. This is 3 computations. I mean, if you want to simulate the SES curve number method, 3 computations per day. This is number of grid points, right. Let us say 5000 grid points, so 5000 computations for a single day simulation, right. So all are correct, depends on the purpose, depends upon the data availability, depends upon the computational resources, right. Do we really need to represent our system like this, or is this sufficient, right? For example, someone was talking about floods in the morning. I don't want to represent the entire process in the catchment. I am interested what is the flow that is coming here at the outlet, so that I can do my flood management plans. So I can consider this to be a lumped if it satisfies, if it gives me acceptable result. So this more discretization increases the realism of the realistic way of representation, but it also increases the computational complexity. So more distributed it is, more computationally complex it is, right. And also your uncertainty, number of parameters, here it is only one parameter. If you take curve number, there is only one curve number. Here there are 3 curve numbers, here there will be 5000, because each is a combination of this, okay. And how do you distribute this will also matter. For example, I have distributed this based on topography. Now some people will say, no, I don't want to distribute based on the topography, I want to distribute between upland and lowland processes. One of the earliest distributed models that was developed was top model, okay. Top model distributes between upland and lowland processes, that is floodplain processes and the upland processes, because hydrology behaves differently at different locations, okay. So depending upon that, how do you classify also makes it this thing, right. So SWAT is a physics based semi distributed model. Why it is semi distributed, I will come to that. Now deterministic and stochastic. Deterministic model is given an input, it will always give the same output. If an input is same, output is going to be same. Stochastic, not necessarily. That may be for a given input, then can be multiple outputs, right. So SWAT is a deterministic physics based semi distributed model. Now coming to the questions, what are the factors that must be considered while selecting a model? Forget about what is there on the slide. How do you choose? How do you choose? Mostly. You join under some faculty for your master's, PhD, see what model is being used in that group and apply it. Yes? How many of you have done that? No one? It's hard to believe. Only one. You people have done it. You have done with me. Right? Here, at least all the people who are working with me do that. I teach what is the purpose of modeling, how to select the model, but my group does not follow it. Okay? That's a different story. Right? But first and foremost is, what is the purpose of modeling? Are you interested in stream flow? Are you interested in the processes that contribute to stream flow? Right? What is the output that you are interested in? Okay. So, for example, if you want to look how different agricultural management practices affect stream flow, affect sediment transport, affect nutrient, then yes, SWAT is a good model. Right? There are other agroecological models, right, which can take care of that. But if you are only interested in doing the flood modeling, then probably not. So, the purpose of modeling becomes important, right? Or if you want to see how much is the reservoir inflows, then probably SWAT is not a good model. But if you want to see how your irrigation practices affect the crop growth, still it's not a good model. You have to go for a crop growth model, right? You really don't want to, if you are only interested in how your irrigation is affecting crop growth, probably go for a crop growth simulation model and it will do your job. Now, which hydrological variables are you considering for the analysis? Are you considering stream flow? Are you considering ET? Are you considering groundwater recharge? Are you considering base flow? So, depending upon that, you need to choose the model. Now, these two are the primary drivers of what models to be chosen. But even though you have these two, there are still n number of models that are available to you. Then comes the data availability. You have chosen the most complex model which can represent everything in a most realistic way, but you don't have the data to be given to input. Will it work? It will not work. So, you need to go back and see what is the data that is available to you. Is the model that you have will work on limited data, or do you need the entire data as it is? Okay? And what are the processes affecting the system? All models do not represent all the processes. So, depending upon that, what kind of process you have. And then complexity of the model, right? Mostly you increase complexity only if it's required. Otherwise, choose the simplest model that is available to you. Don't go for a complex model. Choose the simplest model that is available to you if it serves your purpose. Right? So, the complexity of the model is also something that we need to take care. More complex the model, more parameters, more uncertainty, right, and more this thing. And obviously, when you have a model that is developed that can be used, whether you get assistance to it or not, far too many errors, right? We don't know how to set up a model, right? And unless you have a user community assistance available, it makes your life very difficult, right? So, SWAT model was there, and before the SWAT plus came, there was in between a version of what we call as SWAT grid. I don't know any one of you had heard of it or not. There is a model in between SWAT, which we are using now, and SWAT plus, something called as SWAT grid, which was basically a gridded version of SWAT. Now, it was developed as a PhD work in Germany by one of the scientists, Hendricks. Okay. But then there was no user community assistance available. It was very complex, and that's where it did not click, right? So, that is something you need to have a user manual, you need to have something to know how to run it, you need to have a theoretical documentation before you run. How many of you use the hydrological models? How many of you know what is happening inside it? How many of you have actually read the theoretical documentation? less than 10%, sorry, right? So something that to think about. You should read how it simulates. Unless you read, unless you don't know, you will never make sense of your results, right? It will have no understanding. If you have no this thing, it will never make sense what the results are coming, right? So Professor Chaube said that we intuitively can get to know that your result is wrong. That intuition comes from understanding the process, understanding the model, right? So more you read, more you get to know about it, the more efficient you will do the modeling, but at the same time, more your belief on the modeling will fade away, right? And that is good. You should never believe the output that you are getting is the absolute truth. There is lot of uncertainty, there is lot of simplification that is happening, and that we should be knowing, and that should get reflected in our analysis of results, okay? So this is about the model. The next component is your calibration and validation, okay? Anyone knows what is calibration? It is optimization. That water is there from yesterday, right? Okay. What is calibration? Okay. So we are essentially trying to match simulator to observed, right? Okay. Anyone else? What is calibration? To adjust that of the observed. Okay. It is fine tuning of parameters. Now what is a parameter? Next question. What is a parameter? Components? Unknown state of a system, okay. Processes, okay. Anything else? Relationship between input and output, okay. Yeah, it helps develop the relationship between input and output, yes. All of you are correct, right? So calibration is basically the process of estimating the parameters, right? Now, what are parameters? Parameters are basically used to describe a characteristic of a system, right? Now these can be physical variables. A particular model, saturated hydraulic conductivity, can be a parameter. And at the same time, a parameter can also describe a process within your hydrological cycle, right? I think yesterday someone was talking about ESCO and EPCO. ESCO and EPCO are basically parameters for drawing out the moisture from deeper layers. So it's a process that we have simplified, right? Hydraulic conductivity is a parameter. Is curve number a parameter, or is it a variable? Why is it a parameter? Curve number is fairly defined, no? Curve number is a fairly defined version. Given a land use, given a soil class, your curve number is more or less defined. Why? It is not exactly a variable. It is, there is an uncertainty, even though they have given a particular value for a particular land use and soil. You see, it's very qualitative information, and that is where we adjust. We adjust the curve number a bit. It's one of the sensitive parameters, right? But it's primarily a parameter because of the uncertainty in how we describe it. It's very qualitative nature, okay? And obviously the lumpness. You have a large area, you have a pixel of 30 meter by 30 meter, even if 10 meter by 10 meter is too large, 100 square meters, there will be a huge change. Okay, I think Ashi during her field visit she experienced that, right? There is a huge change in how there will be difference. A variable represents the state of the model and assumes a dynamic nature, right? Any variable, right? It can be time, it can be stream flow, it can be precipitation, right? So variable is where it has a dynamic nature. Now this is the equation. Anyone knows what equation is this? Kostyakov equation for infiltration. I is equal to kT power alpha. There is one more, actually modified Kostyakov equation. I is equal to kT power alpha plus beta. Yes. K and alpha are parameters, I and T are variables. Just to put it this way. Okay. K and alpha are parameters, K and alpha are parameters, I and T are variables. Okay. And we try to estimate K and alpha for the given soil condition. Right. Now, as she said, model calibration is the process of fine tuning these parameters to obtain a model representation that satisfies a pre-agreed criteria, right? Essentially what we try to do in calibration is we try to minimize the error between observed and simulated. Okay? So if it is stream flow, we try to minimize the error between observed and stream flow. Now in this process, what we all do, right? In some cases even I do that, is we tweak the parameter so much that it does not represent the process anymore what is there in the field, right? We tweak the curve number, let us say between 50 to 100, and we have known that that curve number should lie between 65, but in the optimization process that becomes 85 or 90, that means you are completely changing the land use or soil, right? And that is where Professor Chaubey was telling, you always look into the uncalibrated model, results of uncalibrated model. See whether it makes sense, see whether the input that you are given makes sense or not. Unless that makes sense, some of the applications are not valid anymore. Okay? So model parameters are estimated or adjusted by comparing the model output with observed data. One of the example is linear regression, right? Y is equal to mx plus c. M and C are estimated such that sum squared error is minimum. Yes? Y is equal to mx plus c, any linear regression. All of you would have plotted graphs in your lab for a data. You would have drawn a best fit line. How did we draw that? Some random line going between data points. How many of you have done that? Some random line going between the data points, right? Others are not, they also have done it, but they are not accepting it. You need to fit a regression, you need to fit a line. Best fit line is where your error is minimum. It's not a random line drawn along the data. Okay? So that is what you try to minimize this error, and usually the sum squared error, and we are squaring it to avoid positives and negatives to cancel out each other. There may be some positive error, there may be some negative error, and if you sum it up, the positives and negatives may get cancelled out. So to avoid that, we are squaring the error term, right? So some example, a manual calibration approach. This top line is the actual discharge. These are the different simulations you can simulate. So there are different ways of calibrating. One is what we call as manual calibration, where you simulate, then you go and manually change the parameters by seeing the output hydrograph or output of your model to minimize the error, right? That usually comes, like some of the models which take lot of computational time, we go for manual calibration, and that comes with experience. So unless you know the model, or unless you have a clear understanding of the processes of your watershed, manual calibration is difficult. Okay? The other one is automatic calibration, which is based on some optimization algorithm, where we have an objective function of minimizing the error between simulated and observed. This is a case, right? This is something that I have done. This is a performance measure, NSC, and 1,000 number of iterations. I put it through a optimizer called as amalgam, which uses 4 different heuristic algorithms to optimize, right? And initially there will be a variation. It takes the best solution and it tries to come up with the best solution. Okay. So it is a model calibration is posed as an optimization problem. Now, one of the things with these models and model calibration, based on whatever little experience I have, is that everyone uses both model and model calibration as a black box model. You know what is a black box model? What is it? We give an input, it gives an output, no one cares what's happening inside, right? So when we use model calibration and models like that, it is more of a garbage in, garbage out, especially eco-hydrological models. It's true. You don't know what you're giving in, you don't know what's happening, and you're getting output, you're interpreting those results and publishing papers. You know, publish in Journal of Hydrology, WRR, with that garbage in, garbage out data, right? It's entirely possible, right? But then it is important to know what's happening. So many times in this optimization process, your optimizer does not know what is the actual representation of system. Only the modeler knows. Your optimizer does not care whether the curve number of a particular land use is 65 or 80. It adjusts it so that my output is matching, right? So we should be careful while doing auto calibration. Don't take any random parameters and apply and say that these are the parameters. Are those parameters actually reflecting your characteristics, right? For example, clay soil, and if you say my hydraulic conductivity is 40 mm per hour, is it something that can be represented, that is realistic? No, right? But your optimizer may give you 40 millimeters per hour hydraulic conductivity, right? So that is something that I wanted to stress. Now once you calibrate the model, once you estimate the parameters, there is something that we do, validation. Actually, before even we do calibration validation, I think we should start with sensitivity analysis. It comes after this slide, but yeah, actually you start with a sensitivity analysis, identify sensitive parameters, then do calibration and validation. Anyway, we'll come to that. Model validation is you have estimated a parameters which you have seen that, okay, physically this is possible in this particular catchment. Now, are these parameters suitable for a different data set? Right? Let's say you have taken a long-term simulation, 1990 to 2024, and you say that I have calibrated the model between 1990 to 2010, 20 years. You got an excellent NSE, 0.95, 0.96, right? P bias is close to 0, RV is also close to 0, right? R square is close to 1. Is R square a good metric? We all represent R square, right? How many of you have read a paper with R square in hydrology for stream flow? R square. R square is not a good metric to compare hydrographs, right? Don't use R square at all to compare hydrographs. Or R square is not a good metric for any non-linear data. It's only good for linear data. Okay. Anyway, coming back. Now, from 2011 to 2024, you simulate it with the same parameters that you got between 1990 to 2010, and then you evaluate how is the performance of your model. Now, if it is more or less similar to what you got in calibration, that means your model is well calibrated. However, if your model performs completely differently from what it has done in calibration, then you need to go back and relook at your calibration, right? You got a 0.95 NSE, and then in your validation, let's say you got only 0.1, 0.2, or sometimes even negative. That means your model is not even suitable during this period. It cannot be applied. That means any predictions that you are going to do with that particular model is not valid for any other period other than 1990 to 2010. okay, and that is where the model validation becomes important. You need to validate the model to check whatever parameters that you have taken, are they globally applicable to any time period, any data set, right? Okay, so there are different validation techniques. Yeah, this is a good example. Again, something that I have done. I think yes, I have done this. So I have this is a mass curve, a calibration of one of the catchments. You see how closely it has matched. Red is observed, black is simulated. Excellent model, right? But same thing when it goes to validation, you see that there is a large difference, right? So this model is not good. Whatever model that you are getting here, similar results you should get in your validation, right? If it is not getting similar, then you should understand why it's not coming similar. Is it because of there are some changes in your system? Is it because your parameters are overtrained to a particular catchment, or there is something that has completely changed in the watershed, right? And that is where your validation techniques help. One of the most commonly used validation technique is simple validation. You divide the data into calibration period and validation period and just do the simulation and check it. There are other more exhaustive cross validation techniques, leave P out, leave 1 out, then there is k-fold cross validation or 2-fold cross validation, and there is also a bootstrapping method where you randomly generate points, right? Your exhaustive cross validation is mostly used in your machine learning methods. Yes, how many of you are exposed to machine learning? You use mostly this kind of exhaustive methods to train your model, right? There it is known as training the model. Calibration is nothing but training your model. So let's see the simple validation. It's known as holdout validation. Data is randomly split into 2 data sets, training and testing, calibration and validation. Now, when we are splitting the data set, most of us do it randomly. We say 60% for calibration or 70% for calibration, 40% or 30% for validation. In my experience, you don't need to follow that 60, 30, 60, 70, 40, whatever that is. You make sure that whatever the data set you are taking for your calibration, similar characteristics are there in your validation data set. That is, let's say your precipitation, what is your average precipitation, maximum precipitation, mean precipitation, standard deviation, all of them are similar for both. Then your calibration and validation will be good. What it makes sure that when you do that, that means model is trained or calibrated by considering all the possible scenarios that a catchment may have. Now let's say you have this data set, let's say it's a 10-year data set, and you have taken first 6 years for calibration, next 4 years for validation. Now let's assume that out of your first 6 years, 5 years you have received above normal rainfall. That means it's wet years. Now in your validation period, in your 4 years, all 4 years were dry periods. You have trained your model or calibrated your model for wet conditions. It has no way we can expect it to perform in a dry condition. It's a miracle if it performs well. Let me put you this way, right? If it is wet condition and you're calibrating and you're putting it here, then it is. So before we do the calibration, we should split the data, check what are the precipitation characteristics, what is the stream flow characteristics, right? How are they matching or not? How many of you have done this? No one? You have not done it. No one, right? And you have set up the models, yes? That you never checked whether it should be similar. If it's not matching, then you are not splitting it correct. Whole point is your model in calibration should be seeing all the possible variations, and that is being ensured by making sure your statistical parameters in both of them are similar, right? So don't just go in any model training or any calibration, whether it is machine learning or anything. You make sure that your data has everything during your model calibration or training. Unless we do that, our models are not good enough, right? Don't just go ahead and say that first 6 years I will do calibration, next 4 years I will do validation. And if it doesn't work, okay, last 6 years I will do calibration, first 4 years I will do validation. That's what we do, right? Yes? Yes or no? Bhavesh? Right? Okay. There is a k-fold cross validation. Now here what we do is with this, mostly used for machine learning, it becomes too cumbersome to calibrate k-fold validation for a ecohydrological model as big as SWAT, right? But then just to give an overview, you divide the data sets into different what you call subsets. And among these subsets, let's say there are different into 5 subsets. You use 4 subsets for training the model and 1 subset for testing the model, or 4 subsets for calibration, 1 subset for validation. Now you make sure that all the subsets are used at least once for validation, while remaining are used for calibration. Now among this, there are different ways of choosing. One way is you choose which one is the best. Other one is, sometimes what we do is we take the average of parameters that we get in the k-fold cross validation, okay, and you go ahead with that, you check it. Even after this, we sometimes, after we do the k-fold cross validation, we have a completely independent data set. On that we will check how good is our model performing, right? Okay. T would be here, most people are sleepy, but let's continue. Okay. So are you following? Yes? Little bit more energy. Okay. More energy to say yes rather than to sleep. Okay. Right? Okay, let's go forward. Okay, let's coming to performance evaluation measures. When we say that your output and the observed variable should match, how do you check that they are matching? I already told R square is not a good metric, right? So just saying R square is good does not make any sense. R squares will check whether both are linearly matching or not. I hope I have a figure here which has a good R square but is not a good model. So you need to check how a model is performing, but how do we check that? Yeah, coming back to the question. Based on qualitative and quantitative measures. Explain. Okay, how do you quantitatively find errors between observed and simulated? What is error? Okay. Your observed and simulated is a time series, no? Huh. Okay. Okay. Any other method? Graphical representation. Okay. By seeing physically the plot of observed and simulated, we can tell whether the model is good or not. Yes? Okay. Any other method? Descriptive statistics, yes. Whether the descriptive statistics such as mean, variance is matching or not, okay, of your observed and simulated data. Okay, let's go some of them. Graphical evaluation, right? This blue line is observed. I have done this exercise with my MTech second years already, but for others, which one is a good model? Blue is observed, remaining all are simulated. Which one is good? Black one, gray. There is no gray here. There is black. There is black, purple, green, red, yellow. Which one is good? Black. Black is good. Everyone says black. Which one is good? It has nothing to do with hydrology. All of you can tell. Between those four graphs, which one is matching closely? Which one is good? Purple. How many are saying purple? 4, 5. How many are saying black? Okay, more votes goes to black. What about others? You need to have some answer, at least one answer. So graphical representation, this is the issue. It is subjective. Some people felt purple is better because it is matching closely here. Some people felt black is better because it's representing and this part more accurately, right? So graphical way of doing things is basically you have some present some part of your time series or some characteristics of the time series, right? So there are different statistical measures, and one of the descriptive statistics, that's also a good statistical parameters of observed and model time series data. That's also a good way of checking how good they are, right? So there are all of them are residual based metrics. These metrics are divided into absolute metrics, which are quantitative assessment of model error in terms of units of variables. So if it is stream flow, it is cubic meters per second. If it is evaporation, probably in terms of depth, millimeters. If it is soil moisture, again in terms of depth. Relative measures are unitless. Absolute measures you use when you are interested in to find the total error, right? Let's say I am estimating my evaporation to be 6 mm and my absolute measure says that the error is 0.5 millimeters. I want to know how much is the accuracy with which I want. Relative measure is more of a metric which can be used to compare across different watersheds, right, or different processes, different ways of representing things, right. So your relative measures are unit-free metrics where you can compare the errors. Absolute error is basically give you the metric. So a simple example is a 2 mm error over a 1 centimeter measurement is high, whereas 2 mm error in a 1 meter measurement is very low. So in your absolute metric, both will come as 2. But when you go for relative, you know that the 2 mm has less effect on a 1 meter measurement as compared to a 1 centimeter measurement. Okay. So some of the absolute performance metrics are absolute maximum error. What is the maximum error that is there in your entire time series? Each time step you can measure the error. Among those errors, what is the maximum error that you have? Peak difference, wherever the peak is coming, if you are interested in flood, find out the peak difference, that is what your peak difference. Mean absolute error, what is the mean error that you are getting among all the errors that you have? RMSE, root mean square error, another metric which is most very commonly used. Mean error, absolute is your basically removing the sign. So don't consider whether it's positive or negative. Mean error, the positives and negatives get cancelled out. Whereas relative performance errors are relative absolute error. This is based on the flow that is occurring or observed flow, observed variable. Percent error in peak, similar to peak difference, but percentage error as compared to the peak that is there. R square, NSE, and relative volume error. Okay, I think I don't have the difference between R square and NSE, but R square is not a good metric for nonlinear models. So try to avoid it as much as possible. And another take-home message that I want you to take is, when you have different performance metrics, you make sure that you are at least evaluating minimum 2 to 3 metrics. One metric does not give you all the characteristics of your time series. You should have minimum 2 to 3 metrics to evaluate the performance of your model. Don't just report only NSE, don't just report only R square. You see different ways, right? There are different papers. There is a good paper which was published in 2005. Not Abbaspur. It's from the University of Bristol, which tells about, I forgot, probably I'll share it to you, which represents the characteristics of each of these performance metrics. Okay, and what do they mean, right? It's also important to know what do they mean before you go and say evaluate. Your analysis interpretation depends upon these values. Okay. Okay. Still sleepy? Yes. Okay. We are almost about to be done. Let's talk about SWAT, right? Something that we are going to do a hands-on. SWAT, as I said, is a comprehensive physics-based. I wrote distributed, but I would still say it's a semi-distributed model. It simulates hydrology, plant growth, nutrient, and bacteria dynamics. It does a lot. Okay, and it's developed by United States of Department of Agriculture, Texas A&M, right, which currently hosts this model, right, or the development of this model. There's a team of scientists that work on this, right. So SWAT model is not developed by one person. It was conceptuated by one person, but then many researchers, many scientists, many people like you have contributed to development of SWAT. It's an open source model. The code is easily available. If you want to tweak the code, you can do that, right? If you want to do some modifications, that's also possible, right? And many of the Professor Chaube's group has done that, right? They have gone and tweaked the code. They have done it. So this is the evolution of SWAT model, right? It has a long history. It started with setting up experimental watersheds back in 1937, experimental watersheds in Riesel, Texas. Over a period of time, different methods. You have universal soil loss equation in 1965, unit hydrographs in 1940s and 1950s, SCS curve number method in 1972. Then you have Cream's equation for the transport process, right, EPIC model. Then you have SWRRB, right, which is Gleam's model, again all water quality models. And 1990 was the first time the SWAT development took place. So SWAT was developed as a PhD work. SWAT was developed as a PhD work in 1990s. PhD work of Jeff Arnold at Purdue University, right? That is where the SWAT started. And from there, over a period of time, it has been developed. Many people have worked on it. It's a comprehensive model which has integrated so much. The model that you see is a work of more than hundreds of scientists, hundreds of researchers who have contributed to developing the model. Let's say tomorrow you say that I want to improve a particular module. You can go ahead and do that, right? You can develop your own code, you can do that, and you can integrate it into the SWAT model, right? And right now we have something called a SWAT Plus, which was 2018 and which still is getting popularized in now. Okay, It is advanced version of SWAT. It has simplified many of the processes. Core of the SWAT remains same. Core mass balance equation remains same, but the variation comes in terms of the way the data gets represented or the way the files get generated. Okay, they have simplified much of it in SWAT plus, because SWAT generates far too many files. Simulation time is also quite more, right? They have simplified much, and in addition to that, they have also introduced some advancements in how we represent the SWAT. Now, when you say simulation of watershed hydrology, it has two components. One is the land phase, which simulates evaporation, transpiration, infiltration and runoff by considering rainfall and climate variables. It basically simulates the land surface. And the second component is the routing phase. That flow that gets generated, in addition to that, sediment transport, nutrient flow, all of that comes in routing phase, right? So, in the land phase, runoff gets generated based on SCS curve number method or Greenham's method. Evaporation and evapotranspiration is estimated using Penman-Montieth, Hargreaves and Priestley-Taylor method. You have three methods there. Then runoff, when your runoff is done, whatever is the runoff that gets generated from the rainfall remaining goes as infiltration. Okay. Routing phase, the routing of your nutrients happens differently. It considers various advection and dispersion equations, which Professor Chaubey is going to talk tomorrow. And it considers routing in two ways. One is the variable storage routing, that is the reservoir routing, and the second one is Muskingum method, right? Most of the time you go with the default methods. Default methods are variable storage for routing, SCS curve number for runoff, and Penman-Montieth for potential evapotranspiration. But you can go ahead and change whatever is the required. Now, what is the data? I think this is something Ashi has covered. DEM, land use, soil, weather, and some gauge data, basically the stream flow data or sediment data or nutrient data that you have that can be used for calibration and validation of the model. These three components characterize the watershed. Climate is the driving force, rainfall, and gauge data is used for model evaluation, right? So, separate the data requirement for this. Now, let us see how it does, right? When I say that it's a semi-distributed, some people say it's distributed, so how does it do? It takes the catchment and using the DEM, it delineates this catchment into subbasins, right? Subbasins are again completely based on topography. Wherever one stream and another stream meets, it creates a subbasin, right? Now, this subbasin is completely based on topography, based on the DEM, based on the flow accumulation, flow and flow direction. This subbasin will have land use, soil and slope. It will have a land use class, it will have a soil class, it will have a slope class. Now, in all these three, unique combination of these three is what we call as HRU, hydrological response unit. This happens within a subbasin. Within a subbasin, unique combination, that is, you have all raster files which are pixels. The pixels which are overlaying one another, well, those unique combination of land use, soil and slope creates one HRU. Now, up to that point it is fine. Now, what SWAT does is to reduce the computational effort, it removes the interaction between the pixels. For example, let us take this particular subbasin. There is a unique combination which is occurring here close to this point, another unique combination that is occurring little upstream. Now, what SWAT does is SWAT will lump both of them into a single HRU. It takes out the spatial interconnection within a subbasin. Now, like that you will have number of HRUs in each subbasin. It will do the mass balance for each HRU and then sum up the output to the water subbasin outlet. Within a subbasin, there is no routing that is taking place. Whatever the component, hydrological component that you are taking, they get summed up at the subbasin outlet. From there, when they move to the watershed outlet, there will be routing taking place. Understood? Yes? No? That is why I call it a semi-distributed model, because it still lumps up in a particular catchment. But your hydrological response unit is the computational unit at which all the computation take place, which takes the input of solar radiation, climate, and land management practices. You need to give in the data of your crops. You need to give in the data of what are the management practices you are considering. Unless you give that, you are not actually simulating it correctly. Now, once you give that, the output will be in terms of hydrology, in terms of water quality, in terms of bacteria, right? It also has a bacteria module, right? In terms of, it also simulates what is the soil moisture, what is the evaporation, what is the transpiration. Okay? Any doubts? No? From the sub-basin outlet to the watershed outlet, that is where the routing takes place. Okay? Okay. Finally, we are coming to the end of lecture, which you are all waiting for, right? Yes? Someone said very strongly yes. Okay. So, what are the take home messages? Right? Ashi sitting in the front bench is sleeping. So, obviously everyone is. I could see many people's eyes closing, right? Okay. So, what are the take home messages? It's the hydrological models are useful tools to assess the impacts of climate change within a watershed. Obviously, use hydrological models as a tool, right? It all depends on it is the modeler who is important. That is, you are more important than the model. You are the one who are making sense of what it means, right? So, they are simplified versions of real world hydrological systems, right? So, don't expect them to be an absolute truth. They are a simplified version, and you should have that understanding to develop a more clearer system, right? Interpretations will be much better. It's important to choose appropriate model to get effective results, right? Just because we are teaching SWAT in this particular course does not mean we apply SWAT everywhere. Okay? Try to learn new models. There is nothing harm. All of us are reluctant to know new models, right? But come out of that. Calibration is required to estimate the parameters of the model which are specific for the watershed. There is a big discussion whether the calibration is actually required for a model like SWAT or not, but not going into that. Once you start working with SWAT, you will have your own opinion whether the calibration is required or not. But in general, some of the parameters must be estimated because of the uncertainty, because of the lumping of various processes, right, and representation. And model evaluation must be done using appropriate performance measures, right? Just don't do selective reporting in your publications, or when you say that particular model has worked well and this is the performance. Truly evaluate the model. See whether it's working or not. If it's not working, need not be a hydrological model. It can be a machine learning model. It can be a statistical model. If it's not working, look at why it's not working. What is the reason? And that's where the real work lies, right? Otherwise, running this model, you don't need to be a graduate also. Nowadays, high school students can run computer better than us. They can do it. Okay, so it is something to think. It is you who is most important, not the model. It is you who has to make sense of the results that are coming out. It is you who has to make sense of the input data that you are giving. Okay? Okay, with this I will stop and let's have a short tea break. After a tea break, we want to have a hands-on, which is in the computer lab in the civil department. It's a small lab which cannot accommodate all 40 of you together. So, we have split that into two groups, 20-20. I think batches have been sent already. So, the first batch will go from 4 to 5, second batch will be from 5 to 6. We will have a hands-on session on SWAT, probably till the delineation part, and then we will continue. Okay. So, all NIT Warangal students, they know where the lab is. Please help others. Okay. Thank you. Any questions? I forgot. Although we are running out of time. Anyway, I can take a couple of questions. When will you leave? That is the one question. No questions? Okay. Think about it. We can discuss it during the hands-on. Yeah, Aradhana. Mm-hmm. It's very difficult to answer that because I have not seen the data, I have not seen what you have done, right? Whether probably what inputs you are considering. It's a machine learning model, learning models, you need to consider what inputs, whether there is a correlation